polynomials. So we have done something like this earlier using another method to find the root, remember? So something like that. So let's say you have a polynomial crossing the line. The polynomial fx crossing the line. The place, excuse me, the place that it crosses the x-axis is called the root, the point, the x value. So this is the x value, the actual root, not root, root, actual root. You can approximate the actual root. So you have points x2, x1, and x0. Let's say this is the approximation. So once you bring this approximation closer to the actual root, the approximation becomes more closer, right? So this is going to be a more closer approximation. Closer approximation. So the Newton-Raphson's method also uses Taylor's theorem to develop the formula. Let's say if x1 happen to be, let's say, if x1, x0 plus h, h can be something like a step, a small variable. Okay, it's a very simple, it's a variable. Be the exact root then let's say if x1 is the exact root of the curve fx, if you plug in x1 into that equation, that will give you 0, isn't it? Okay, so therefore expanding fx0 plus h by Taylor series so this is the Taylor series from the last time, remember? Taylor series expansion. Fx0 plus h step size, first derivative, fx0 divided by 1 factorial, and then h squared second derivative 2 factorial plus h cube triple prime okay, and so on. Since h is small, h is a small step. You can neglect for example, if h is a very small number, 0.01 or something, then h squared will be much smaller, isn't it? H squared will be 0.1, z. H is squared, so and so on. H cube will be much smaller, isn't it? So you can ignore all these higher orders. You can ignore them because they are almost zero. So you can go ahead and ignore all this, all the higher order. If you do that, then you're going to get, somebody has the mic on. So you're going to end up getting it fx naught it's going to be fx naught plus h f prime x naught. Okay, so if remember, if this is a root, then the equation must go to 0. Any question? Then solving for h, gives minus fx naught divided by f prime x naught. In that case, a closer approximation to the root is given by x1 was a x1 plus h, right? And now it's going to be, with h replaced, you're going to get fx naught, f prime x naught. Similarly, starting with x1. Once you have found x1, then you can first, initially you started with x0. Okay, initially you started with x0. And then you found x1 using this formula right here. Initially you started with x0. Using this formula, you find x1. After you find x1, then you can find x2 using x1. But still better, approximation x2 is given by x1 minus okay, and so similarly x2 can be found with x2 minus. So each iteration will improve the accuracy of the root. Sorry, x2. And so on. You can keep on going at as many iterations you want. So now we look at an example to see how to apply this formula to find out the root. In general, xn plus 1 is xn minus fxn which is known as the Newton-Raphson formula. X cubed minus 2x minus 5 equal to 0. So let's go ahead and find the root. Let fx equals to x cubed minus 2x minus 5. To begin with, you don't know where this is going to cross the x-axis. So you need an initial guess. So you need an initial guess. If it's not given, you need an initial guess. If this is the polynomial is crossing the line, we don't know where is it exactly crossing, but we can find an initial guess. We can find an interval. For example, giving you the idea. Let's say this is the actual root. Okay, it's crossing somewhere here. And this is the actual root. So actual. And you can find an initial guess. You can say find an initial guess. You can either do anywhere, on the left side, on the right side, or any side you like. So once you have the initial guess, before you do the initial guess, you can also find an interval. So how do you find the interval? This is how you find it. Let's generate a table of values for the function. So this is a polynomial function x cubed minus 2x minus 5. X value, we can start from 0, 1. It's up to you, you can start from -1. But I'm going to start from 0, 1, 2, and so forth, and 3. Then plug into the function. F0 is -5. F1 is equals to 1 minus 2 minus 5 is equals to -6. F2 is 8 minus 4 minus 5. So -1. 3, 27, -6, -5. So again, we get +16. So what do? You stop now because you have a sign change. You can see there's a sign change here. Sign change from negative to positive. That means a change of sign means the curve moved from year to year. It has moved from year to year, crossing the x-axis. So you have a root in that interval. X1 is x0 minus fx0 divided by f prime x0. Okay. Fx, you already know what is fx, isn't it? I mean, from earlier. Fx prime is 3x squared minus 2. So x1 is going to be x0 minus You can plug in the x. 2, 8, 2 cube, 8 minus 4 minus 5. 8 minus 9 is minus 1, minus 1 over 10. 2 plus 10. 2 plus 1 over 10 is equal to 2.1. So your x1 is 2.1. You started with x0 is equals to 2. Is equals to 2. Next you calculate for n equals to 1. So that's going to give you x2 is x1. So using the previous value to calculate more closer value. X1 is 2.1. Using the value we just calculated here. So it's the same equation as before. Instead of using 2, right now we are using, so instead of using 2, we right now are using 2.1. Okay, X2 is 2.0946. Why don't you guys calculate X3? Each one of you calculate X3. So when you calculate now, you try to keep this problem, I'm keeping 4 decimal places. We know the answer is around 2, but we would like to keep at least 4 decimal places. So x3 Okay, if you do this carefully in your calculator, you'll get 2.0946. So you can note that it's not changing anymore. There's no change from the previous value. So if you're calculating this to 4 decimal places, maybe if you calculate this to 10 decimal places, it might change. But if you're happy with this, you can stop. No change. There's no change from previous iteration. Therefore, x1 is equals to x2 is equals to 2.0946. Although this is not really accurate, but I think this is approximation. So the required root something like this. So this is the root. Any question? Any question? Another example, using a Newton's method or Newton-Raphson's method, Raphson's methods, they're the same. Find the smallest positive root. So now same thing as before. So you have a root. Then you want to find the interval. You just test 2 points. In this case, then I'm getting 1 and -3. That's a sign change. 0, 1, I'm here. One minus 3, I'm here. So you have a line passing, doing this, going through like this, and this is the root. The root. So the interval from here, what is my interval? Interval is the x values, okay, not y values. You look here, what is the interval? Maybe I've written this wrong here. Your interval,
Oh, okay.
I apologize on this. Interval is 2 and 3, x values.
3.
So what is the interval here? G?
Is 0, 1, sir.
Good. So the interval is 0 and 1. Because in this interval, that's y value sign is changing. Sign changes. So the interval, this is the interval. Sorry about that. Interval. So just now we chose 2 as our initial guess based on this interval. So you guys remember earlier on, so my interval was 2, 3, so I chose 2 as my initial guess. Because the root is lying somewhere in between this. So what is your initial guess? If this is your interval, what will be your initial guess? So you can choose, in this case, I'm choosing my initial guess to be somewhere in between. You know, you can choose 0, 1, okay, for convenience, integers. But if you choose something very close to the actual root, you can quickly converge to the solution. So let x naught be 0.5 in this case. So using this formula, so that's going to give you xn minus fxn is xn cubed minus xn cubed plus, so no, sorry, no minus there, xn cubed minus 5xn plus 1. And then, so what is the derivative of this? Okay, remember this is fxn, this is right here. So what is the derivative of fxn, f prime xn? Derivative of the numerator is 3xn squared minus 5. Okay. Any question? Confusion? Confucius? No?
No, sir.
Okay, if you like, you can simplify this algebraically. So that later on when you plug in numbers, it'll be much easier to crunch numbers. So we cross multiply. Don't put a big cross. People might be thinking, later student might be thinking, why I crossed that out? Cross multiply. So it's going to be xn this and this cancels. And then you will end up getting two xn cubed minus 1. So if you simplify it, it's better. So later on, when you plug in numbers, especially if there are many decimal places, then number crunching becomes very difficult. So your x1 is going to be 2x0 cube minus 1 . So we're talking about small numbers here. X1 is represented in 6 decimal places. That's very important. Then you keep as many decimal places, at least 6 decimal places in this case. Okay. Because it's a small number. To find x2, you use the same equation with x1 plugged in. And then you do the next iteration, x3. So any questions so far? This is your x1, and still there's no sign of convergence. This is 0.16471. This is 0.201568. And then you keep on going until there's no change. So x3 using the same formula, but with x2 plugged in. Next, you calculate x4. X4 0.201640, smallest root. So you can see it's not changing from here to here. Now we can be very positive, because let's say if you're keeping just one decimal place, if you're just keeping one decimal place, you'll get 0.2 here. Okay, if you're keeping one decimal place, you also get 0.2 here, then 0.2 here. You just keep one decimal place, then you already made an early conclusion it's not changing. You would have made an early conclusion that it's not changing if the decimal places are too small. So that would have been a wrong conclusion. You will end up with a very very crude approximation. Therefore, the smallest root correct to 6 decimal places Any question?
No, sir.
No, sir.
No question? We start the next question. Solve x log base 10x given the initial value x naught is 10. Okay, for simplicity, we just write log base 10 is log x, right? We know when something is written just as log without a base, it's understood it's a log base 10. Initial value given so now you define your function. We define the function. If you subtract 12.34 on both sides, then you will end up getting a function x log base 10x. In that case, I'm just going to write this first. Okay, base 10 minus 12.34 is equal to 0. Then you can just call this fx. Any question? Any question? Are you guys still online?
No, sir. Yes,
Yes,
sir.
sir.
No.
Yes, sir.
Okay, you know that, just for a quick review, you know that the derivative of natural log x is equals to 1 over x, correct? So what is the derivative of a log base 10x? It's equals to what? So log base dx is what? Is 1 over log b, 1 over natural log b multiplied by x. Do you guys agree with this? Therefore, f prime x is, you apply the product rule on this, call this u, and then you call this v, applying the product rule, the derivative, this will go to 0, isn't it? So the derivative of x log 10x will be x multiplied by 1 over 10. Sorry, natural log 10 times x. I mean, it's not part of natural log. Maybe I should put the x in front. 1 over plus log base 10x. These two cancels. These two cancels, and then you get 1 over natural log 10. 1 over natural log 10 as log base 10x. That's equals to now you use the formula. Fxn I'm just going to put log for log base 10. So I'm going to just put log for log base 10. So these things are basically same as log x. Okay. These are same as log x. It's understood. It's log base 10. So again, if you like, you can do the cross multiplication and simplify them. So later on, number crunching becomes easier. So if you cross multiply this, if you guys cross multiply this, you'll get this. If we simplify, this and this will cancel. Okay, any questions so far? Any question?
No,
You
sir.
guys are still on. Any question? No.
No, sir.
Okay, thanks. So now you find out what is x1 with the initial guess given to you. Multiply by 10. So initial guess, value 10 was given. Six three two 409. So I'm keeping 6 decimal places here. And the next two, use the same formula. Using the same formula. Okay, there's no change. You see, I'm using the same formula as here. Use the same formula, but except right here, this changes and this changes. That's all. It will be 11.63. The x1 that you just calculated, 11.632 2409. 11.632409. That would give you x2. This is the iteration 1, the iteration 2. Next iteration is x3. Is same formula. These are just repetitive work. So you have to be very sure that you do the number crunching. So X3, the only thing that changes is what's inside the parentheses here and here. Point, you plug X2 value here. So you take them, make sure you know your calculator can do these things. I myself was using the calculator from the calculator accessory from the desktop. So if you compare these two, if you guys compare this with just 4 decimal places, we just compare this for 4 decimal places, you have met the target. You can see, if you could just compare the 4 decimal places, you met the target. But if you want 6 decimal places, so then you have to continue more iterations. But I'm going to stop here for this particular reason. Let's say if I go and check the difference between the X3, the difference between X3, we take X3 minus X2, absolute value, and find out what it is. This X3, let's say this is X2, 59. X2 value 594868. X3 11.594852. Subtract 0.000016. So it's very small, quite small, right? Quite small. If you're happy, you can accept this as the solution because the difference is so small from the previous one. It is almost not changing. Therefore, I'm going to accept it. Very small change. Therefore, after 3 iterations, X value 11.5948. So I'm going to accept my answer correct to 4 decimal places because for 2 reasons. One is there's a very small change if you compare for 6 decimal places, or you see for 6 decimal places. Small change. if you're talking or comparing the previous ones, previous iterations. But if you look at just to 4 decimal places, there's no change. The question didn't ask you to go up to 6 decimal places, but I think 4 decimal places sufficient. So the reason why 4 decimal places is sufficient is up to you. If you, depending on what you're working on, what kind of problem. So this is really 11 is really a big number. It's not 0.00 something 11, and 4 decimal places is quite acceptable here, but that depends on what problem you're working on. So if you want to stop at correct to 4 decimal places, so the exam, if it's given to you, it will be specified, you know, how many iterations you're supposed to do. The answers are required correct to how many decimal places and so on. So as far as for correct to 4 decimal places, there's no change. You can see there's no change. Okay. So based on this, I'm accepting it as an approximation, as a good approximation. Any question? Any question?
No, sir.
No, sir.
No, sir.
If,